Welcome back to Sleepy Orbits. It's late, the room is dark, and if your mind won't quite switch off yet, that's all right. You're in good company tonight. Tonight, we're going to find the closest black hole to Earth. In 2022, astronomers discovered one sitting just 1,560 light-years from your bed, close enough, in galactic terms, to call our own neighborhood, and it holds the record. It is the closest black hole ever found. But here's the thing most people don't realize. It is almost certainly not the closest one there is. Our galaxy holds an estimated 100 million black holes, and nearly every one of them is dark, silent, and invisible, which means the true closest black hole to Earth has never been found. Some careful estimates suggest it could be within 80 light-years of where you're lying right now, and nobody knows which patch of sky it's hiding in. Tonight, we're going to hunt for it properly, and by the end, the dark between the stars is going to feel less like something watching you and more like something sleeping. One thing before we begin. If you fall asleep partway through, good. That's the point. In the morning, tell me in the comments the last thing you remember hearing. And if you make it to the end, tell me which part of the search for the closest black hole stayed with you and what you'd like us to explore next. If these nights help you rest, a like or a subscribe helps this channel more than you'd realize. Now, let's begin. Start with the one we've actually caught, because the story of how we found it tells you everything about why the rest are still hiding. In the constellation Ophiuchus, the serpent bearer, there is a small, ordinary star, a little cooler and dimmer than our sun, the kind of star nobody would ever look at twice. A few years ago, a spacecraft called Gaia noticed something wrong with it. The star was moving in a T-circle, not drifting the way all stars drift, but swinging around and around once every 6 months or so, the way a dancer swings around a partner. And when astronomers looked for the partner, there was nothing there. No second star, no glow, no shadow, nothing at all. Just an empty point in space, and an ordinary star bowing around it, again and again, in a loop about the size of Earth's orbit around the Sun. From the size and speed of that loop, you can weigh the invisible partner, and the answer came out to roughly 10 times the mass of our Sun. There is only one thing in the universe that can be 10 times heavier than the Sun and give off no light whatsoever. In 2022, a team led by a young astronomer named Kareem El-Badri confirmed it. The empty point has a name now, Gaia Black Hole 1. And it is the closest black hole human beings have ever found, 1,560 light-years away. To feel how close that is, remember the scale of the thing we live in. Our galaxy is 100,000 light-years across. The giant black hole at its center, the one everybody has heard of, the monster called Sagittarius, a star, is 26,000 light-years from here. This new one is 17 times closer than that. On a map of the whole galaxy, Gaia Black Hole 1 and our Sun are pressed against each other, 2 dots sharing the same quiet suburb, and the light arriving from its companion star tonight left around the time the Roman Empire was falling. In galactic terms, that's not the distant deep, that's across the street. And now the honest part, the part that turns tonight from a fact into a mystery. That black hole, our record holder, was found because it happened to keep a visible star as a companion, a lantern swinging around it, giving it away. Almost none of them are so considerate. Astronomers estimate our galaxy has made about 100 million black holes over its lifetime, roughly one for every 1,000 stars that ever formed, and of those 100 million, we have found, in total, a few dozen. The rest are simply dark. They orbit the galaxy exactly like stars do, silent, starless, 60 kilometers wide, radiating nothing. And if you spread 100 million of them through the galaxy's disk the way the stars are spread, the mathematics says the nearest one to us right now is probably not 1,500 light years away. It's probably within about 80 light years. That's 20 times closer than the record holder. On the galactic map, it isn't even across the street. It's in the yard. Somewhere out there, closer than most of the stars you can name. There is almost certainly a sphere of pure darkness the size of a small city, circling the galaxy on its own patient orbit, and no telescope on Earth or above it has ever laid eyes on it, because there is nothing to lay eyes on. That's the real subject of tonight, not the black hole we found, the one we haven't. Let's take a moment to feel that distance properly, 1,560 light years, because after our last journey together, you've earned the right to judge cosmic distances like a local. Light, you'll remember, crosses from the moon to your eyes in about 1 1/3 seconds, from the sun in 8 minutes, from the nearest star in 4 years and 3 months. The light arriving tonight from the record holder's companion star has been traveling for more than 15 centuries. When it left, the Western Roman Empire was collapsing. No one on Earth had ever printed a book, and every city you've ever visited was either a village or a forest. That's real distance, no question, more than 300 times deeper than the crossing to Alpha Centauri that broke all our engines last time. And yet, on the galaxy's own map, it's remarkably little. Our sun lives in a quiet residential structure called the Orion Arm, a spur of stars and gas, maybe 3,500 light years wide, one of the smaller ribs of the Milky Way's spiral. Gaia, black hole. One lives in it with us. Same arm, same suburb, same slow orbit around the same distant downtown. The galaxy is 100,000 light years across, remember, so this record-setting gulf of 1,500 light years amounts to about 1.5% of the way across the map. If the Milky Way were a great city 30 miles wide, the closest confirmed black hole would be sleeping about 700 meters from your house, walking distance, and the unfound one, the statistical neighbor we're really hunting tonight at 80 light years, would be in the apartment directly upstairs. Before we go hunting, let's be sure we know what we're hunting, because the black hole in your imagination, the one from the movies, the roaring whirlpool, devouring everything in reach, is not what's hiding in our neighborhood. The real thing is quieter, smaller, and much stranger. A black hole begins as a star, and not just any star, a giant, something at least 20 or so times the mass of our sun. The kind of star that burns blue-white and lives fast. Stars like that spend their whole lives in a tug-of-war. Gravity pulls every atom inward, trying to crush the star into a point, and the furnace at the core pushes outward, holding the collapse off hour by hour for millions of years. The star survives only as long as the furnace burns, and the furnace always runs out. When a giant star's core finally exhausts its fuel, the outward push stops in a moment, like a hand lifted from a spring, and gravity, which has been waiting patiently for millions of years, wins in less than a second. The core collapses. The outer layers detonate as a supernova, one of the brightest events the universe can stage. And at the center, if the core is heavy enough, something extraordinary happens. Matter is crushed past every barrier physics can offer. Past the strength of rock, past the strength of atoms, past the strength of the particles inside atoms, past everything, until all of it, several suns' worth of material, has collapsed into a region so small and so dense that its gravity closes over it like water over a stone. A boundary forms around the collapsed core, a perfectly spherical surface of no return, and we call that surface the event horizon. Inside it, the escape velocity, the speed you'd need to leave, exceeds the speed of light. And since nothing can move faster than light, nothing leaves. Not rock, not radio waves, not the brightest flash of the brightest bomb. Light itself falls back like a thrown ball. That's all a black hole is in the end. A place where gravity has won so completely that the exit has closed. Here's the part that surprises people. They're small. A black hole of 10 solar masses, 10 entire suns worth of matter, has an event horizon about 60 kilometers across. 60 kilometers. That's the size of a metropolitan area, a half-hour's drive at highway speed, holding the crushed mass of 10 suns. If you replaced our sun with it, the sun that fills the daytime sky, it would shrink to a black dot you could hide behind a mountain range. And that smallness matters enormously for tonight's hunt, because being small and dark in a galaxy this large is the best camouflage that exists. Astronomy runs on light. Every star chart, every catalogue, every photograph of the sky ever taken is a record of things that shine. A dormant black hole doesn't shine. It doesn't reflect. It doesn't glow in infrared like a cooling ember or crackle in radio like a pulsar. It emits, for all practical purposes, nothing at all. A 60-kilometer sphere of perfect black, adrift among the stars, is not merely hard to see. It is, in the ordinary sense of the word, unseeable. You could point the largest telescope humanity has ever built directly at one, hold it there for a year, and record nothing but the stars behind it. Now, you may have seen those glorious pictures, the glowing orange rings, the brilliant jets, black holes lit up like furnaces, and you might reasonably ask how something invisible got so photogenic. The answer is that we have only ever photographed black holes in the middle of a meal. When a black hole has a close companion star close enough to touch, its gravity can peel gas off the star's surface, and that stolen gas doesn't fall straight in. It spirals like water around a drain, forming a flat, whirling disk. Friction inside the disk heats the gas to millions of degrees, and it screams in X-rays as it goes down. And that scream is what our instruments catch. A feeding black hole is one of the brightest objects in the galaxy, but feeding is rare. It requires a victim close at hand, and most black holes have none. They finished their violence long ago in that one founding supernova and have drifted ever since with nothing to eat, no disk, no glow, no scream. Astronomers call them dormant, which is a gentle word for it, sleeping. The galaxy's 100 million black holes are almost all asleep, and a sleeping black hole is about as dangerous and about as detectable as any other patch of empty sky. That's what we're looking for tonight. Not a monster in mid-roar, 100 million closed eyes, one more foundation stone, and it's the one the movies get most wrong. A black hole is not a vacuum cleaner. It doesn't reach out. It doesn't pull harder than anything else its size. Outside the event horizon, a black hole's gravity is exactly the gravity of any other object with the same mass. If some cosmic magician swapped our sun tonight for a black hole of precisely one solar mass, here is the complete list of what would happen to Earth's orbit. Nothing. The Earth would continue on its path to the meter because gravity only cares about mass and distance, and neither would have changed. The sky would go dark, and the world would begin to freeze, which is its own quiet catastrophe, but nothing would be pulled in. The planets would circle a black point forever, as stable as they have ever been. Falling into a black hole is genuinely difficult. Space is almost entirely empty. The targets are 60 kilometers wide and everything is moving at tens of kilometers per second sideways, which is precisely why things orbit instead of falling. Keep that in your pocket for the rest of the night. The 100 million sleeping black holes of our galaxy are not hunting. They can't hunt. They just orbit the way stars orbit, dark stones in the same great river, and the galaxy has been carrying them safely for billions of years. It's worth telling the life story of the star that became our neighbor, because a black hole is a biography with the last page showing, and the earlier pages are glorious. Long ago, in some bright nursery of gas along this same spiral arm, a giant was born. A star of perhaps 30 or 40 solar masses. Stars like that are the aristocracy of the galaxy, and they pay for it. Where our sun rations its fuel across 10 billion years, a 30 solar mass star burns with such fury that it exhausts itself in just a few million, less than 0.1% of the Sun's lifespan. It would have shone tens of thousands of times brighter than our Sun, blazing blue-white, its surface a storm of wind so fierce it shed whole suns' worth of its own body into space over its lifetime. If Earth had existed nearby, that star would have been visible in daylight, and it lived, in cosmic terms, for a long weekend. A few million years of extravagance, fusing hydrogen to helium, then helium to carbon, then onward up the periodic table, each new fuel burning hotter and faster than the last, carbon for centuries, silicon at the very end for about a day. A day. The final act of a great star's chemistry runs on a kitchen timer. Then the core turns to iron, and iron is the one element that gives nothing back when fused. The furnace's first truly dead ash, and the story we told earlier begins. The push stops. Gravity wins. The core, a ball of iron the size of the Earth, collapses to a point in less than a second. The outer body detonates, and for a few weeks, one star outshines the combined light of 100 billion others. If that supernova happened today at the record holder's distance of 1,560 light-years, here is what you would see. A new star would appear in Ophiuchus, brighter than Venus, bright enough to notice at twilight, possibly bright enough to glimpse in daylight. And it would hang there for weeks before slowly fading over months. No harm would come to us. The danger zone for a supernova is generally reckoned at less than 100 light-years, and this would be 15 times beyond it. It would simply be beautiful and a little solemn, the visible death notice of a giant. Our ancestors saw such things and wrote them down. Chinese astronomers in the year 1054 recorded a guest star in Taurus that shone for 2 years and left behind the Crab Nebula, whose collapsed heart still spins there today, 30 times a second, sweeping the sky with lighthouse beams of radio. The sky over your roof has staged this show before, and it will stage it again. And each performance plants another dark seed in the neighborhood. In fact, astronomers keep a short list of the likeliest next performers, and the headliner is a star you may know by name. Betelgeuse, the red shoulder of Orion, visibly orange to the naked eye, is a supergiant in its final act, swollen so large that placed where our Sun is, its surface would reach past the asteroid belt. It has already run out of hydrogen. Somewhere in its core, the countdown chemistry we just described is underway, and sometime in the next 100,000 years, possibly far sooner, possibly tonight, the light of its collapse will arrive here. When it does, at its distance of around 500 or 600 light-years, comfortably outside any danger, Betelgeuse will flare to rival the full moon, a single point of light bright enough to cast shadows and read by, visible in broad daylight for weeks, before fading over months and leaving Orion forever missing a shoulder. Its core is probably a shade too light to seal itself into a black hole. The models favor a neutron star, rung 2, but either way, the nearest famous star, Death on the calendar, is a reminder that the sorting machine never stopped. The constellations, you know, are not finished objects. They're a slow furnace, mid-burn, and the sky you fall asleep under is still manufacturing its darkness, which raises a question worth settling before we go further. Not every dead star becomes a black hole, and the sorting rule is one of the most elegant in astronomy, a ladder with 3 rungs, decided almost entirely by mass. A star like our Sun, when its fuel runs out billions of years from now, will shed its outer layers gently and leave behind its exposed core a white dwarf, an Earth-sized ember of crystallizing carbon dense enough that a teaspoon weighs tons, held up forever by the sheer refusal of electrons to be crowded further. That's rung 1, and it's where more than 97% of all stars end. No explosion, no horizon, just a long, quiet cooling that will outlast the present age of the universe. Heavier stars, those born above 8 or so solar masses, blow apart as supernovae, and their collapsing cores crash straight through the electron's refusal, crushing protons and electrons together into a ball of nearly pure neutrons. That's rung 2, a neutron star, and it may be the most extreme object you can actually stand to look at. A full sun and a half of matter packed into a sphere the size of a city, spinning in some cases hundreds of times per second, with a surface gravity 100 billion times Earth's. A teaspoon of it outweighs a mountain range. But even neutrons have a breaking point. Pile more than about 2 or 3 solar masses onto that city-sized ball, and no force known to physics, not one, can hold the surface up. There is no rung 3 material, there's just rung 3, the collapse that doesn't stop, the object we've been discussing all night. So when you look at the sky's population of remnants, you're seeing a great sorting by birth weight, countless white dwarfs, millions of neutron stars, and, rarest of all, the 100 million heaviest cases, the ones that fell all the way through. Rarest of all, and even so, common enough that one is probably closer to you tonight than the stars of the Big Dipper. The galaxy has been running this sorting machine for 13 billion years. It adds a new black hole, somewhere in the Milky Way, perhaps every few centuries. Slowly, patiently, one biography at a time, the dark population grows. And let's close the ledger on the question a late-night mind inevitably asks next. Could our own sun ever join them? The answer is no, and it's not a probably no or a reassuring rounding no. It's a flat, physical impossibility. The arithmetic simply forbids it. The sun carries barely a 20th of the mass needed to end as a black hole, and there is no process, none, that can add the missing 19/20ths. 5 billion years or so from now, the sun will swell, shed its outer layers into a glowing shell, and settle down as a white dwarf, rung 1 of the ladder, an Earth-sized jewel of crystallizing carbon that will spend the following trillions of years doing nothing more dramatic than slowly dimming from white to amber, to red to dark. No collapse, no horizon, no hole where the sun used to be. Whatever black holes exist in Earth's long future, every one of them will be a distant stranger, because the one star that could ever truly matter to this planet is permanently, structurally disqualified. The sun isn't just unlikely to become a black hole, the sun doesn't know how. Here's something that surprises almost everyone. The idea of the black hole is older than the United States. In 1783, an English country clergyman named John Michell, a quiet polymath who also more or less invented the science of earthquakes in his spare time, sent a paper to the Royal Society with a thought experiment inside it. Escape velocity was well understood by then, the speed you need to leave a body's gravity for good, and Michel simply asked the question no one had thought to ask. What if a star were so large that its escape velocity exceeded the speed of light? Light, he reasoned, would rise from its surface like a stone thrown upward, slow, stop, and fall back. The star would go out from the universe's point of view. He called them dark stars, and he even predicted, in 1783, exactly how we would find them, by watching luminous stars that wobble around unseen companions. Sit with that for a second. The method that found Gaia Black Hole 1 in 2022 was sketched by a country parson 239 years earlier, before electricity, before the word scientist existed. The idea then went to sleep for more than a century, dismissed as a curiosity, because the physics of light seemed to forbid it. It woke up in the worst place imaginable. In the winter of 1915, Albert Einstein published his general theory of relativity, the new law of gravity, and among its very first readers was Karl Schwarzschild, one of Germany's finest astronomers, who at that moment was serving as an artillery officer on the Russian front of the First World War. In the trenches, between calculating shell trajectories, Schwarzschild worked out the first exact solution of Einstein's equations, the gravity around a single compact mass, and mailed it to Einstein, who was astonished anyone had solved it at all. Inside Schwarzschild's mathematics sat a strange radius, a boundary where the equations seemed to break, time freezing, space pivoting, the surface we now call the event horizon, and whose size still bears his name. Schwarzschild never learned what he'd found. He contracted a disease at the front and died months later, at 42, believing the strange radius was a mathematical artifact, as did Einstein, as did nearly everyone for decades. The objects were simply too outrageous to believe in. It took until 1939 for physicists to show that a sufficiently heavy dying star really would collapse past that boundary with nothing to stop it, and even then the result was largely ignored, its lead author moving on to other work which happened to be directing the Manhattan Project. Only in the 1960s, when the X-ray sky opened and strange violent objects demanded explanation, did the idea finally stand up and stay standing. And it got its modern name almost casually, when the physicist John Wheeler, tired of saying gravitationally completely collapsed object in lectures, took up a phrase from the audience: black hole, 2 syllables, and the most reluctant idea in physics finally had a handle the whole world could grip. From a parson's dark star, to a soldier's dying mathematics, to a lecture hall nickname, The strangest object in the universe was discovered 3 times on paper before anyone found one in the sky. Nature had been keeping 100 million of them in our galaxy the entire time, patiently waiting for us to believe our own arithmetic. So how do you find something that cannot be seen? The history of the hunt is really the history of 3 tricks, each cleverer than the last. And it's worth walking through them in order because each one drew the map of darkness a little closer to home. The first trick was to listen for the scream. In the 1960s, instruments lofted above the atmosphere began picking up X-rays from deep space, which was a surprise in itself because X-rays means something is furiously hot, millions of degrees, far hotter than the surface of any normal star. One source in particular, in the constellation Cygnus, the Swan, blazed brighter in X-rays than almost anything else in the sky, and it flickered wildly hundreds of times a second, which meant the thing producing it had to be tiny. Whatever it was, it sat in a tight orbit around a huge blue supergiant star. And when astronomers weighed the invisible partner by the swing of the visible one, the number came back far too heavy to be anything that shines. That object, Cygnus X-1, roughly 7,000 light-years away, became the first black hole most of the scientific world accepted as real. It was so contentious at the time that Stephen Hawking famously bet against it, wagering with a fellow physicist that it would turn out to be something else. And years later, as the evidence piled up, he conceded the bet, publicly and cheerfully. The scream trick worked. Over the following decades, it found black hole after black hole, each one betrayed by the glow of a star being slowly eaten. But notice what that trick can never do. It can only find the feeders. For every black hole caught mid-meal, thousands upon thousands drift with nothing to eat and nothing to say in X-rays. For half a century, our entire catalogue of black holes was a list of the loud ones, and the loud ones are freaks, rare systems where a black hole and a star ended up almost touching. It's as if you tried to census a sleeping city by listening for noise. You'd find the one house with a party going on and conclude the city held a few dozen people. The quiet 100 million would never appear in your notebook. And the nearest feeder we ever found, a modest system in the constellation Monoceros, sat about 3,000 light-years away, and for decades that stood as the closest black hole known. Not because nothing was closer, but because nothing closer happened to be eating. Which brings us to the false dawns. And I want to tell this part honestly because it's one of the best cautionary tales in modern astronomy. In May of 2020, a team of respected astronomers announced something electrifying. A star system just 1,000 light-years away in the southern sky, so close and so bright you can see it with your naked eye, appeared to contain a quiet black hole. The headlines wrote themselves. The closest black hole to Earth, sitting in plain sight, in a system anyone could step outside and point to. For a while, it was one of the most famous objects in the sky, and then other astronomers did what astronomers are supposed to do. They looked again. Over the next 2 years, independent teams re-observed the system with sharper instruments, and slowly the black hole dissolved. What had looked like a star swinging around an invisible heavyweight turned out to be something rarer and more delicate. 2 stars caught in a fleeting stage of their lives, one of them stripped almost bare by the other, puffed up and faint, mimicking the signature of an unseen third body. In 2022, the original team and their critics published together gracefully, and the verdict was final. 2 stars, no black hole. The closest black hole to Earth was once again nowhere to be found. Around the same time, another nearby candidate, a red giant with an invisible partner, nicknamed the Unicorn, suffered a similar fate under similar scrutiny. The pattern was clear, and it taught the field a hard lesson. Darkness is easy to imagine and hard to prove. When your evidence is a wobble and an absence, nature has more than one way to fake it, and a stripped, dim star can impersonate a black hole well enough to fool the best instruments on Earth for a while. Understand what that moment felt like, because it sets the stage for what came next. By 2022, astronomers knew from the arithmetic of dead stars that the galaxy had to be full of sleeping black holes. They knew the nearest ones should be close, far closer than any feeder in the catalogue, and yet every attempt to actually catch one, quiet and dark, in our own neighbourhood, had either found nothing or found a mirage. 100 million sleeping giants, and not one confirmed specimen sleeping. The problem needed a different kind of trick altogether, not listening for screams, not chasing wobbles in a handful of promising systems, something colder and more patient, a way to weigh the darkness around every star in the sky at once, and let the black holes give themselves away not by light, not by appetite, but by the one thing they cannot turn off: gravity. And as it happened, the perfect machine for that trick was already flying. Since the sleepers hold their secrets so well, it's worth appreciating just how spectacular the exceptions are. The rare black holes that do have something to eat, because they include the most luminous objects the universe has ever produced, and they prove a point that matters for tonight. Darkness for a black hole is a choice made by circumstance, not by nature. Feed one, and it becomes a beacon visible across the cosmos. The gentlest version is the kind we met in Cygnus, a black hole slowly sipping wind and gas from a too-close companion star, wrapping itself in that million-degree whirlpool of a disk. Scale it up and you get the quasars, the feeding supermassive black holes in the hearts of young galaxies, single objects outshining their entire host galaxy of 100 billion stars, visible from 10 billion light-years away, powered by nothing more exotic than matter falling down a hole and heating up on the way. When astronomers first catalogued quasars in the 1960s, the energies seemed impossible, and it was black holes, the reluctant idea itself that turned out to be the only engine efficient enough to run them. Gravity, it turns out, is the best fuel in the universe. Falling toward a black hole releases energy far more efficiently than nuclear fusion does. The brightest lights in creation are powered by the darkest objects in it, and there is no contradiction, only diet. And sometimes the diet arrives all at once, in an event so dramatic, it has become its own branch of astronomy. In the center of most galaxies, stars swarm thickly around the resident supermassive black hole, and every so often on timescales of tens of thousands of years per galaxy, one star's orbit wanders a fraction too close. What follows is called a tidal disruption event, and it is exactly the fate we keep insisting can't happen to Earth, happening to an entire star somewhere it can. The black hole's gravity gradient, the same stretching force will keep a safe distance from later tonight, exceeds the star's own ability to hold itself together. And over a few hours, a sun that had burned peacefully for billions of years is pulled into a long ribbon of glowing gas. What one astrophysicist memorably described as spaghettification at stellar scale. Half the ribbon escapes into space. The other half spirals in, igniting a flare of light that can outshine the galaxy's core for months before fading. Telescopes now catch several of these per year in galaxies far away, each one a complete stellar funeral observed from a safe seat. I tell you this partly because it's among the most awesome spectacles in modern astronomy, and partly for the reason underneath. Every tidal disruption event we've ever recorded has happened in the crush of a distant galactic center, where stars are packed thousands of times more densely than here, around black holes millions of times heavier than our local sleepers. Out here in the galaxy's calm suburbs, around city-sized 10-sun black holes, with the nearest stars light years apart, the arithmetic of such catastrophes simply never comes due. The universe absolutely does contain the violence your imagination suspects. It keeps it downtown, 26,000 light-years away, in neighborhoods no star of ours will ever visit. The suburbs get the sleepers, and the sleepers get the silence. The machine was called Gaia, and it deserves a few quiet minutes of its own because it may be the most underrated spacecraft ever flown. Gaia was launched by the European Space Agency at the end of 2013, and it did not take pretty pictures. It did something almost absurdly simple instead. It measured where stars are. That's all. Position, distance, motion for nearly 2 billion stars over and over and over, spinning slowly in the dark 1.5 million kilometers from Earth, sweeping the entire sky every couple of months for more than a decade. Its precision is the kind of number you have to walk around a few times. Gaia could measure the position of a star to within a few millionths of a second of arc, which is roughly the width of a coin seen from the distance of the moon. Watch 2 billion stars that carefully for years, and the sky stops being a photograph and becomes a film. Every star is moving. streaming around the galaxy, drifting past its neighbors, and, here and there, wobbling. Because if a star has a companion, anything with mass, a planet, another star, or something dark, the two of them swing around their shared center of gravity, and the star's path through the sky stops being a straight line and becomes a slow spiral, a corkscrew traced across the years. The wobble tells you the companion is there. The size of the wobble tells you its mass. And the beautiful, ruthless part is this: the companion doesn't need to shine. Gravity works in the dark. Gaia was a machine for weighing the invisible, pointed at the entire sky at once. Now picture the haystack. 2 billion stars, and among them an unknown handful, maybe a few dozen, maybe a few hundred, wobbling around something dark and heavy. Kareem El-Badri, the astronomer who found our record holder, has described his own work as exactly that. A search through hundreds of thousands of candidate wobbles, almost all of which turn out to be ordinary, 2 stars, a star, and a faint dwarf, a data glitch, a mirage. He had personally helped debunk several of the earlier false alarms, including the famous naked eye one, so he knew better than almost anyone on Earth how darkness lies. And then in the Gaia data, in the direction of Ophiuchus, he found the wobble that wouldn't die. An ordinary star, about 90% the mass of our Sun, tracing its slow corkscrew 6 months per loop. Follow-up telescopes measured its speed, swinging toward us and away month after month, exactly as the wobble predicted. Every alternative was tested, and every alternative failed. If the dark companion were 2 dim stars huddled together, their combined light would show. It didn't. If it were a dead white dwarf or a neutron star, the mass would be far too low. It wasn't. The companion weighed in around 10 suns, and it shone at exactly 0. In November of 2022, the team published with a title almost defiant in its plainness, announcing a sun-like star orbiting a dormant black hole. This time, it held. The skeptics attacked it, as they should, and it held. Gaia Black Hole 1 was real, the first certain member of the quiet 100 million ever caught, and the closest black hole to Earth ever confirmed. Spend a moment inside that system because it rewards imagination. Picture a world there, a planet circling that ordinary yellow-orange star, the way Earth circles the sun. The daytime sky would look utterly familiar. One warm sun, one blue-black dome. But the night sky would carry a secret. Somewhere among the constellations there would be a patch about the size your thumbnail covers at arm's length, where the stars are subtly wrong. Not missing, wrong. A black hole bends light around itself, so the stars directly behind it would be smeared into faint arcs, doubled, shifted. A tiny circular funhouse mirror hanging silently in the dark, drifting through the constellations as the black hole moves along its 6-month orbit. There would be no glow, no disk, no menace, just that small lens of distortion, the only signature a sleeping black hole ever writes. And the strangest part is that a civilization on that world could go thousands of years without noticing. The distortion is subtle, visible only to careful instruments, 10 suns worth of night hanging one Earth orbit away from their home star, and it would take them until their equivalent of the 20th century to discover it was there at all. And here's the detail that keeps Gaia Black Hole 1 interesting to professionals long after the headlines. It shouldn't exist. Work the story backward. The black hole weighs about 10 suns, so it was born from a star of perhaps 30 or 40 suns, a blue monster. But its companion, the little yellow star, orbits at roughly the distance of the Earth from the Sun, and a 30 solar mass star, late in its life, swells into a supergiant far larger than that entire orbit. The little star should have spent millennia inside its dying companion's atmosphere, spiraling inward, and by every standard model of binary evolution, the pair should have merged or been flung apart long before the black hole ever formed. Yet, there they are, calm as a clock, the survivor and the ghost, in an orbit that theory says is too tidy for the violence that made it. Perhaps the giant shed its bulk early. Perhaps there were originally 3 stars and the system rearranged itself. Perhaps our models of how giants die need repair, which would be the most interesting answer of all. The closest black hole we've ever found came with a puzzle attached, a note from the universe saying politely that our textbooks on the deaths of great stars are not finished. The first specimen from the sleeping 100 million, and it's already telling us we don't fully understand how they're made. Once the first one was real, the dam began to leak. Within months, the same team confirmed a second Gaia Black Hole 2, a red giant star about 3,800 light-years away, circling another silent 10-sun companion, this time on a leisurely orbit of more than 3 years. 2 specimens, both in our broad corner of the galaxy, both found the same way by weight alone. And then, in April of 2024, came the one that made astronomers sit up straight. In the constellation Aquila, the Eagle, about 1,900 light-years away, an old giant star was found tracing a wobble so large that the dark thing pulling it had to weigh 33 suns. 33. Gaia. Black hole. 3 is the most massive stellar black hole ever found in our galaxy, a true heavyweight of the quiet kind, and it is the second closest black hole known, sitting just beyond the record holder. Before this, black holes that heavy were things we only knew from gravitational wave chirps in distant galaxies, colliding billions of light-years away. Now one was essentially next door, asleep, and its companion star carries a signature that gives the story real depth. The star is ancient and almost bare of metals, the chemical fingerprint of the galaxy's first generations, formed more than 10 billion years ago, before the Milky Way had properly finished assembling, which means the black hole beside it is a fossil, a relic of the galaxy's violent childhood, born from one of the earliest giant stars that ever lived here, drifting quietly through our neighborhood ever since, while the sun and earth formed, while life began, while all of it happened. This thing was already old, already dark, already circling. When astronomers found it, they weren't discovering something new. They were noticing something that has been passing through the neighborhood for 10 billion years. There's one more specimen worth meeting because it's the loneliest object in this whole story. Every black hole I've described so far kept a companion star, a lantern, and the lantern is what betrayed it. But most of the 100 million probably have no lantern at all. They drift alone. And a lone black hole gives you no wobble to measure, no orbit to weigh. Nothing except for one last trick, the third and subtlest trick in the hunter's book. Gravity bends light. So if a lone black hole, by pure chance, drifts exactly between us and some distant background star, the star's light gets focused, like a magnifying glass passing over a candle. And for a few months, the background star swells in brightness, then fades back as the dark lens moves on. Astronomers call it microlensing, and it's a lottery. You can't choose when or where it happens. You can only watch millions of stars and wait. In 2011, a star toward the center of the galaxy brightened and dimmed in exactly that lensing signature, and something remarkable happened alongside. The star's apparent position shifted, a tiny sideways nudge as the lens's gravity steered its light. The Hubble Space Telescope tracked that nudge for over a decade, 11 years of patient measurement of one star's position, and the verdict, confirmed and reconfirmed, is that the lens was a black hole of about 7 solar masses, roughly 5,500 light-years away, with no companion, no disk, no star, nothing. Just a lone sphere of dark crossing the galaxy by itself, caught only because it happened to walk across a lit window. It remains, to this day, the only isolated black hole humanity has ever confirmed. One out of an estimated tens of millions like it. That's the census so far. The loud feeders, a few dozen. The quiet companions, a handful and counting. The lone drifters, exactly one, caught by luck. The hunt has barely begun. But here's what makes tonight a particularly good night to be telling you this. The hunt is about to leap forward on a schedule, and the schedule says soon. Gaia, the wobble machine, stopped taking new observations in January of 2025. Its fuel spent after 11 years of scanning. But the great majority of what it saw has never been released. The mission's data comes out in enormous curated waves years apart, and the next wave, the fourth great release, is expected around the end of 2026, containing the full harvest of wobbles from more than a decade of watching 2 billion stars. The first 3 black holes leaked out early, found in preliminary slices of that data. The fourth release is the whole ocean. Astronomers publishing their forecasts expect it to surface dozens more dormant black holes, perhaps more, each with a measured mass and a measured distance. And there is no reason to believe the current record will survive. Somewhere in that unopened archive, statistically speaking, there is very likely a wobbling star closer than 1560 light-years, quietly corkscrewing around something dark, its discovery already recorded, waiting in a queue to be noticed. The closest black hole we've ever found may already have been observed years ago by a spacecraft that's now retired, and the number that breaks the record is sitting tonight on a server in Europe, unread. Within a couple of years, the map of the dark around us is going to be redrawn, and everything in tonight's story is, in the most literal sense, the before picture. The lensing lottery deserves a closer look before we move on, because it's about to stop being a lottery. Understand first why the odds are so cruel. For a lone black hole to reveal itself this way, it must pass almost perfectly between Earth and a background star. And perfectly is nearly the right word. The alignment has to be finer than 1,000th of a second of arc, the width of a human hair seen from thousands of kilometers away. The galaxy is generous with stars but stingy with alignments. That's why surveys don't watch one star, they watch fields of hundreds of millions night after night, mostly toward the galaxy's crowded center, where the backdrop is densest, and they wait for any single star to brighten and fade in the smooth, unmistakable curve of a gravitational lens rather than the jagged flicker of an ordinary variable star. It's fishing with a net the size of the sky. A ground survey in Poland and Chile, running for decades, has logged thousands of lensing events this way, and nearly all are caused by ordinary dim stars drifting across the field. The art is in the exceptions. An event that lasts months instead of days means a heavy, slow lens. A heavy lens that emits no light of its own, checked and rechecked in every wavelength, means a corpse. That's how the lone drifter in Sagittarius was caught, and why confirming it took 11 years of follow-up. The difference between a heavy dim star and a true black hole comes down to measurements at the very edge of what our finest instruments can do. Now, for the part that changes the game. Late this decade, if schedules hold, an observatory called the Nancy Grace Roman Space Telescope is due to launch, and one of its principal missions is exactly this: staring at the galactic bulge continuously, with a camera whose single view is 100 times wider than Hubble's, measuring hundreds of millions of stars with space-grade precision every few minutes for months at a stretch. The forecasts are startling. Where the ground surveys caught one confirmed lone black hole in a generation, Roman's planners expect its micro-lensing campaign to catch lensing events by the tens of thousands, and among them, if the population estimates are right, dozens upon dozens of isolated black holes, each one weighed and placed on the map. Between Gaia's final data release opening the census of the companioned sleepers and Roman netting the lone drifters, the next 10 years are set up to transform the black hole map of our corner of the galaxy from 3 confirmed points and a guess into a real chart with dozens of addresses, and every year the chart fills in. The statistical ring around our own neighborhood tightens. The hunt For the actual closest one, the one in the apartment upstairs, has stopped being a dream and become a schedule. So let's do what the telescopes can't, and go looking for the one that's actually closest. We can't see it, but we can reason our way toward it, and the reasoning is lovely. Start with how black holes are born. Only the giant stars make them, and giant stars are rare. Roughly 1 star in 1,000 is born heavy enough to end as a black hole. But the galaxy is old, and it has been making and burying giants for 13 billion years. Run the arithmetic on all the generations of stars that have ever lived and died here, and you land on that number we keep circling, on the order of 100 million black holes in the Milky Way. Now ask where they are. Giant stars are born in the galaxy's disk, in the same spiral arms and stellar nurseries as everything else, and when they collapse, their black holes mostly stay in the family, orbiting the galactic center in the same great flow as the stars, with the same neighborhoods, the same suburbs, the same downtown. Some get kicked. A lopsided supernova can fire its newborn black hole off at hundreds of kilometers per second, and those wander into lonelier orbits. But the majority ride the disk, which means the density of black holes around us should roughly track the density of stars around us. Count the stars in a sphere around the sun, take 1 out of every 1,000 or so, adjust for the ages and histories, and the estimate falls out. In a sphere 80 or so light years across, centered on your bedroom, there should be, on average, about one sleeping black hole, sharing the volume of space that holds our few thousand nearest stars. Some nights it's closer than that average, some centuries it's farther. These things drift, but the expectation is stubborn. The nearest black hole to Earth is probably closer than the brightest stars in your sky. Sirius is 8.5 light years away, Vega 25, the stars of the Big Dipper mostly around 80 to 100. The nearest black hole is likely somewhere in that last neighborhood, camouflaged against the dark between stars whose names we've known since childhood. Why haven't we found it if it's that close? Because everything about it conspires to hide it. It is, remember, perhaps 60 kilometers wide, the size of a city, at a distance where entire stars are points of light. It emits nothing our instruments can catch. If it has no companion, it makes no wobble. If it happens to drift across a background star, it would announce itself in a micro-lensing flare. But the sky is enormous, and such perfect alignments for any single black hole happen perhaps once in hundreds of thousands of years. The truth is that a dormant black hole 80 light years away is harder to detect than a candle on the moon. Enormously harder. The candle at least emits light. Our nearest dark neighbor could hang there for another million years without giving us a single photon of evidence, and the only ways we'll ever catch it are patience, luck, and gravity. Perhaps a future Gaia, watching the sky 10 times more precisely, will notice a handful of stars near one patch of Cygnus or Lyra, all deflected by a fraction of a whisker, the gravitational wake of something unseen passing through. Perhaps a micro-lensing survey will win the lottery, or perhaps it will simply never be found in your lifetime or mine, and the nearest black hole to Earth will remain what it is tonight, a statistical certainty with no address. I should mention, for completeness, the strangest idea anyone has published on this subject, because long-time listeners will hear the echo. A few years ago, two physicists asked a mischievous question about the outer solar system. You may remember from one of our earlier nights together that something out beyond Neptune seems to be herding the most distant icy worlds into strange, clustered orbits. The mystery usually called Planet 9. The standard guess is a hidden planet, 5 or 10 Earth masses on a vast, dark orbit. But the paper pointed out that the evidence is purely gravitational. We've never seen the thing, only its pull, and gravity doesn't say what's pulling. So they ran the numbers on an alternative. A primordial black hole, one born not from a star, but from the crushing densities of the first second after the Big Bang, could in principle have been captured by our sun long ago. A primordial black hole of 5 Earth masses would be about the size of a grapefruit-sized abyss orbiting our own sun, hundreds of times farther out than Neptune, herding the ice worlds. I want to be clear about the status of this idea. It is speculation, published, peer-reviewed, taken half seriously as these things go, but speculation, and most astronomers still bet on a planet if the pattern is real at all. The reason I bring it up isn't to alarm you, it's the opposite. Even if it were true, even if the nearest black hole to Earth turned out to be inside our own solar system, a grapefruit at 400 times Neptune's distance, the effect on your life on Earth, on every planet, would be precisely what it's been for 4 billion years. Nothing. It would just orbit the way everything orbits. The mass is the mass, whether it's a planet or a hole, and the solar system wouldn't feel the difference. That's the recurring lesson of tonight, and we're about to make it explicit. And since we're entertaining dark companions, here's a story most people have never heard about the time science seriously proposed that the sun itself had one, and then went looking and settled the question properly. In the early 1980s, paleontologists studying the fossil record noticed something eerie. The great mass extinctions of Earth's history seemed, in their data, to arrive on a rough schedule once every 26 million years or so, too regular, they argued, for chance. Astronomy was asked for a mechanism. And in 1984, physicists offered a dramatic one. Suppose the sun is not single. Suppose it has a companion, a dim red dwarf or a failed star, on an immensely long, stretched orbit, spending most of its time a light year or more away, and once every 26 million years swinging inward through the Oort cloud, scattering comets toward the inner solar system like a hand dragged through a beehive. Earth's extinctions would be the bombardment's signature. They named the hypothetical companion Nemesis, the Death Star, And for a while it was a perfectly respectable idea, published in the best journals, argued at the best conferences. Notice how closely it rhymes with tonight's theme, a massive, dark, unseen thing, hiding not 80 light years away but in our own solar system's attic, shaping life on Earth across deep time. If a black hole in the Big Dipper's neighborhood unsettles you, Nemesis was that fear with a schedule attached. Here's why the story is comforting rather than chilling. We checked. That's the whole point of the story. A dim companion within a couple of light years would be faint in visible light, but it could not hide its warmth. Any object heavier than a large planet glows in the infrared, unavoidably, and so astronomers surveyed the entire sky in exactly those wavelengths, most decisively with a space telescope called WISE, which between 2009 and the early 2010s mapped the infrared heavens hundreds of times more sensitively than anything before it. The verdict was clean. No Saturn-sized body hiding out to 10,000 times the Earth-Sun distance. No Jupiter or brown dwarf out to 26,000 times. No Nemesis. The Sun is single. The extinction schedule has since largely dissolved into statistical noise, and a 40-year-old ghost story ended the way the best ones do, with a floodlight and an empty room. Hold that alongside tonight's black hole hunt, and you see the pattern of the age we live in. The dark ideas get proposed honestly, because the dark is genuinely there. And then, one survey at a time, the dark gets audited. Sometimes the audit finds a real sleeper, a wobbling star in Ophiuchus. Sometimes it finds nothing, and nothing is its own kind of gift. Every year, the sphere of space around your bed that has been checked, weighed, and found quiet grows a little larger. Fear shrinks the way frontiers do, map by map. The same auditing spirit once weighed an idea far grander than Nemesis, and it's worth a minute because it would have changed tonight's entire story. For decades, physicists have known that most of the matter in the universe is invisible, the famous dark matter, 5 times more of it than everything that shines, detectable only by its gravity. And in the 1990s, one candidate explanation was almost charmingly simple. What if dark matter is just black holes? Not the stellar kind, but primordial ones, formed in the crushing first instance after the Big Bang, in every size from mountains to moons to suns, salted through every galaxy in unimaginable numbers. If that were true, the halo of our own Milky Way would be a blizzard of dark spheres, and the nearest one might be absurdly close, not 80 light years, but a fraction of one. So astronomers tested it with the lensing trick, and the logic was gorgeous. If the galaxy's halo were full of black holes, then stars in the neighboring Magellanic Clouds should constantly flicker as dark bodies drifted across their light. Teams watched millions of those stars for years. The flickers came, but only in handfuls, thousands of times too few. Verdict, delivered across the 90s and refined ever since. Whatever dark matter is, it is not a swarm of star mass black holes. The halo is not a blizzard, and the population around us is the modest stellar one we've been counting all night. One sleeper per 80-ish light years, not one per light month. A small window remains for primordial black holes lighter than any star could make, asteroid mass wisps that surveys can't yet rule out, and some physicists still tend that flame. But the headline stands, and it's a lullaby in the form of a data table. We asked, seriously, whether the darkness around us might be 100,000 times more crowded than it looks. The universe answered no. Before we take our imaginary trip out to visit one, spend a few quiet minutes riding along with the neighbor itself, the unfound one, because its existence, hour by hour, may be the most peaceful in the universe. Picture it from up close, if the word close can apply. A sphere of blackness, 60 kilometers wide, smoother than anything ever manufactured, the single simplest object physics allows. Stars have weather, storms, cycles, songs of vibration running through their bodies. A dormant black hole has nothing. Mass, spin, and silence. That's the complete inventory. It does not flicker because there is nothing to flicker. It does not cool because it holds no heat to lose. It does not age in any way you could measure from outside. The one nearest us has been exactly what it is tonight, without a single eventful day, for perhaps 1 billion years, perhaps 8 billion, and it experiences its existence, if that word means anything here, as pure motion. It falls around the galaxy. That's all it does. Like the sun, like every star you can see, it rides the great carousel of the Milky Way, circling the distant center at something like 200 kilometers every second, one full lap every couple of 100 million years. It has made that lap dozens of times. On its previous circuit, the Earth it was quietly accompanying belonged to the dinosaurs. The Himalayas didn't exist, and the North Star of that age has long since drifted from its post. The lap before that, life on our world had not yet ventured onto land. The neighbor noticed none of it, of course. It swept on through the arms and the gaps, through star nurseries whose light couldn't touch it, and past dying giants whose explosions couldn't move it. 60 kilometers of finished business, weathering nothing, wanting nothing, the galaxy's most complete example of being done. And relative to us, it barely moves. This is worth knowing, because the mind's eye tends to give dark things speed and intent. Stars in the sun's neighborhood and the black holes salted among them all orbit the galaxy together, the way traffic flows together down a highway, and the differences between lanes are small. Typically 20 or 30 kilometers per second of drift between any two neighbors. At those relative speeds, the map of the local sky rearranges on scales of tens of thousands of years. Our unfound neighbor, at 80-ish light years, is going nowhere fast. Across your entire lifetime, it will drift, relative to the sun, by a distance that light covers in a few days, a rounding error on its address. Across all of recorded human history, it has moved relative to us, less than a single light year. It has been roughly where it is now in whatever constellation currently disguises it, since before the pyramids, since before agriculture, since before anyone looked up and organized the stars into hunters and bears and rivers. Every human being who has ever slept beneath the night sky slept beneath it. This same specific silent sphere, unnamed in every language that has ever existed. And the drift it does have is not toward us in any meaningful way, any more than the Big Dipper is falling on your house. It's traffic, all of it, flowing the same direction around the same center on a road 200,000 light years around, with lane changes measured in geological ages. There has never been a calmer neighbor in the history of neighbors, because here is the question. Underneath the whole night, the one your nervous system has probably been asking since the first minute. If there's a black hole within 80 light years and 100 million in the galaxy, should anyone be afraid? Let's take the fear seriously and walk it all the way through, with numbers, because the numbers are where the fear goes to rest. First, remember what a black hole cannot do. It cannot reach. Its gravity at any given distance is identical to that of a star of the same mass at the same distance. There are stars within 80 light years of Earth, hundreds of them, some far heavier than 10 suns worth, and you have never once lost sleep over their gravity, because at that range the pull is beyond negligible. It's not small, it's cosmically comic. The gravitational tug of a 10 solar mass black hole 80 light years away is trillions of times weaker than the tug of the book on your nightstand. Distance doesn't just weaken gravity, it crushes it by the square. And interstellar distances, as we learned on our journey to Alpha Centauri, are the deepest distances there are. We spent a whole night together once on how impossibly far away the nearest star is, how the emptiness defeats every ship we could ever build. Tonight, that same emptiness changes sides. The gulf that keeps us from touching the stars is exactly the gulf that keeps the dark things from touching us. The prison, it turns out, has always also been the wall of a fortress. But suppose one came closer. This is a sleep channel, so let's do the scary thought experiment properly and gently, and watch it fail to be scary. Suppose the nearest black hole weren't 80 light years out, but 1 light year drifting through the Oort cloud's borderlands. Effect on Earth, none. The sun's grip on us is millions of times stronger at that range. Astronomers would be ecstatic. The object would be the discovery of the century, and your commute would not change. Bring it to Pluto's distance then, 40 times the Earth-Sun gap, deep inside the solar system. And genuinely absurd stroke of cosmic bad luck. Even there, its direct pull on Earth would be thousands of times weaker than the sun's. Over centuries, its passage would gently disturb the outer planets' orbits. Comets would be scattered. The solar system's long-term bookkeeping would need revision. And the night side of physics departments would never sleep again. But no ocean would leap, no ground would shake. and the black hole itself, 60 kilometers of perfect black at 5 billion kilometers, would be utterly invisible to your eyes. The honest dangers only begin when something passes within a few Earth-Sun distances, close enough to genuinely rearrange orbits. And the odds of that are where the comfort finally becomes mathematical. Stars pass near the Sun all the time on cosmic schedules. The next notable one, a small red dwarf called Gliese 710, is due to brush the outer Oort cloud in about 1.3 million years, and even that famous close call is a graze at more than a light month. Genuine deep intrusions, something plunging among the planets, happen to a star like ours, perhaps never in its whole 10 billion year life. Black holes are 1,000 times rarer than stars. Multiply the rarities. Earth has existed for 4.5 billion years, every one of those years spent swimming in a galaxy of 100 million black holes. And in all that time, through the age of trilobites, and the age of dinosaurs, and the age of us, not one has ever come close enough to leave a mark on the geological record. The night sky you were born under is the same safe arrangement it's been since before there was anyone to look at it. And there's a final, almost funny layer of safety that nobody mentions. Even if you removed all the distance, a stellar black hole is a surprisingly bad apocalypse. It's 60 kilometers wide. Space is so empty, and everything in it moves so fast, sideways, that even a black hole passing directly through a star cluster mostly hits nothing. Things fall around massive objects, not into them. That's what an orbit is, the endless, successful missing of a target. For a black hole to actually swallow the Earth, it wouldn't be enough for one to wander near. It would need to hit us, dead on, a 60-kilometer bullseye and an 8,000-mile target, in a shooting gallery where the nearest shooter is 80 light years away, has no aim, no appetite, and no motion toward us. Astronomers have estimated odds for events like this, and they come out so small that the universe is expected to end several times over before the ticket is drawn. You are in more danger from your own pillow. This is the strange gift of tonight's subject. We went hunting for the closest black hole, the most fearsome object in the popular imagination, and what we actually found at every step was distance, indifference, and sleep. 100 million of them, and the grand total of harm ever done to us across the entire history of the world is 0. Since the real ones keep their distance, let's close that distance the only safe way there is, in imagination. Come aboard one more impossible ship, the kind we sail to Alpha Centauri, and let's actually visit a sleeping black hole, the nearest one, wherever it is. The journey out is the journey you already know, years of falling through nothing. The sun dwindling behind you to a bright point among points. But this time, the destination refuses to arrive. That's the first strange thing. Approaching a star, you'd watch a point of light swell slowly into a disk, into a furnace, into a sky-filling fire. Approaching a dormant black hole, you watch nothing swell into nothing. Your instruments insist the mass is dead ahead, 10 suns of it, the pull growing month by month, and the view out the window remains a perfectly ordinary starfield. The thing simply isn't there to see. And then, at some point in the final approach, you notice the stars behaving badly. A constellation dead ahead looks subtly squeezed, its stars pushed apart around an empty center, and as you close in, the effect sharpens into one of the strangest sights physics permits. The background stars smear into thin arcs curving around a central blankness, and at the right distance the arcs join, and you find yourself looking at a ring. A perfect circle of bent starlight, light from stars directly behind the hole, folded around both sides of it at once and delivered to your eyes. Astronomers call it an Einstein ring. Inside the ring, blackness. Not the blackness of night sky, which always carries some faint dusting of stars, but absolute optical silence, a disk of pure absence. That's the event horizon's shadow. That's the only portrait a sleeping black hole will ever sit for. A ring of stolen light around a hole in the sky. Park in orbit, a nice wide one, and everything is calm. This is worth saying clearly, because the movies suggest otherwise. In a circular orbit at a respectful distance, thousands of kilometers out, you'd feel nothing unusual at all. Weightless, coasting, the ring of light turning slowly outside the window, silent as a photograph. You could stay for a lifetime. Time itself would run very slightly slow for you compared to the folks back home, a few parts in a million. Less than commercial air travel does to your schedule in the other direction, nothing you'd ever feel. The famous horrors of black holes all live much deeper, and it's honest to name them from a distance. Descend far enough, and gravity's gradient becomes real. The pull on your boots, exceeding the pull on your shoulders, gently at first, then insistently, and for a small black hole like this one, that stretching tidal force would become lethal well outside the horizon. Physicists, with their gift for gallows poetry, named the end state of that process spaghettification. And it is exactly what it sounds like, and we are not descending there tonight. Hold instead at the safe rail and consider the boundary itself, because it's stranger than any violence. The event horizon isn't a surface. There's no crust, no membrane, no wall. It's a place in space, marked by nothing locally at all. A falling probe would cross it without a bump, without a flash, without any sensation marking the moment, and yet, from that moment on, every path it could possibly take, at any speed, in any direction, leads inward. It's not that escape is forbidden by some force, it's that outward has stopped being a direction. Down becomes the future itself, as inescapable as tomorrow. And you, watching from your safe orbit, would never even see the crossing. The probe's image would slow as it approached the horizon, its clock visibly crawling, its light stretching redder and dimmer, until it faded from view like a coal going out, frozen forever from your point of view, in the act of arriving. Time dilation isn't a special effect down there, it's the ordinary weather. What's inside nobody knows, and I mean that in the deepest sense available to science. Our best theory of gravity, Einstein's, predicts that everything crossing the horizon is carried down to a central point where density and curvature run to infinity, and physicists don't believe that answer, not because they have a better one, but because infinities in a theory are usually the theory's way of confessing it has reached its limits. What actually holds at the center of a black hole is a question for the marriage of gravity and quantum mechanics, a theory we don't have yet, which means every black hole in the sky, including our unfound neighbor, is a sealed envelope containing the deepest secret in physics, guarded by the one perfect lock in nature. Nothing that learns the answer can ever come back to tell. There's something almost restful about that at the end of a century that has explained so much. The universe keeps a few rooms locked, even from its most determined guests, and it keeps 100 million of them in our galaxy alone, quiet, patient, and shut. There's one more way humanity has learned to perceive black holes, and it deserves its place in tonight's story, because it's the most astonishing of all the tricks, and it changed the hunt forever. Everything we've talked about so far, wobbles, lensing, X-ray screams, still rides on light. But in 2015, after decades of engineering that many considered quixotic, physicists in the United States switched on an instrument called LIGO, two enormous L-shaped detectors, each with arms 4 kilometers long, capable of noticing when the length of those arms changed by less than 1/10,000th the width of a proton. Why build such a thing? Because Einstein's theory predicts that when massive objects accelerate violently, they shake the fabric of space itself, sending out ripples, gravitational waves that stretch and squeeze everything they pass through by almost nothing, but not quite nothing. And in September of 2015, within days of switching on, the instrument shuddered. Both detectors, 3,000 kilometers apart, rang with the same waveform, a rising chirp lasting 1/5 of a second. Decoded, it was the signature of two black holes, 29 and 36 times the mass of the Sun, spiraling into each other and merging in a galaxy over 1 billion light years away. For 1/5 of a second, that collision radiated more power than all the stars in the observable universe combined, none of it as light, all of it as pure vibration in space. And 1 billion years later, the ripple, by then unimaginably faint, passed through the Earth, through you, had you been born yet, and two machines in Louisiana and Washington state felt it. Since then, the detectors have logged hundreds of these events. Black holes colliding across the deep universe, each one invisible to every telescope, each one perfectly audible, if that's the word, in gravity. We've learned that black holes of 30, 50, 80 solar masses are common out there, that they pair up, that they merge, that the universe hums with their collisions at all times. The population we can't see keeps announcing itself in the one signal that darkness cannot muffle, because it isn't made of light at all. It's made of the same thing the trap is made of: gravity betraying gravity. And the gravitational sky has only begun to open. In 2023, several teams around the world announced something even stranger than the chirps. For 15 years they had been timing pulsars, those city-sized lighthouse corpses from rung 2 of our ladder, whose radio pulses arrive with the regularity of atomic clocks. Dozens of pulsars scattered across the whole sky, monitored for a decade and a half, function together as a galaxy-sized detector because a passing gravitational wave subtly disturbs the arrival times of every pulse. And the timing showed a pattern, all the pulsars everywhere wavering together in a slow, correlated sway. The interpretation, still being refined, is extraordinary. It's a background hum, the combined rumble of supermassive black hole pairs, millions to billions of suns each, slowly circling each other in the cores of merging galaxies all across the universe, their waves overlapping into a permanent ocean swell of space-time, passing through everything, always, including you, tonight, at this moment, stretching and squeezing you by less than the width of an atom's nucleus, ceaselessly, since before you were born. And in the 2030s, if plans hold, a mission called LISA will unfurl 3 spacecraft into a triangle millions of kilometers across, lasers linking them to hear that deep register in detail. We began this part of the story with black holes as the most invisible objects in existence. We're ending it in a universe where their voices, at every scale, from 10 sun chirps to million sun choirs, turn out to be playing constantly, a music beneath matter that we only learned to hear in the last 10 years, and that was here, humming under the floor of the world all along. It's worth pausing on the contrast between our quiet local specimens and the famous giants, because people tend to file all black holes in one drawer, and the drawer contains creatures as different as minnows and whales. Everything we've hunted tonight is a stellar mass black hole, the corpse of a single star, 10 suns, 30 suns, 60 kilometers across. But every large galaxy, ours included, keeps one black hole of an entirely different order at its heart. Ours, Sagittarius. A star holds a bit more than 4 million solar masses packed into a region smaller than Mercury's orbit, and we've had our portrait of it since 2022. That soft, orange donut of glowing gas assembled by a planet-spanning network of radio dishes. We gave that monster its own full night together some time ago, so tonight I'll say only the part that belongs to this story and one scene from its discovery, because it's the single most beautiful piece of evidence in all of black hole science. For nearly 3 decades, 2 rival teams, one led by Reinhard Genzel in Germany, the other by Andrea Ghez in California, aimed their telescopes at the exact center of the galaxy and simply watched the stars there, year after year. And the stars at the center do something no other stars in the sky do. They whip. One of them, catalogued as S2, traces a complete orbit in just 16 years, and at its closest approach it moves at nearly 3% of the speed of light, an entire sun slung around an invisible point like a stone on a string. Plot the orbits of a few dozen such stars and they all bend around the same empty spot, and the mass required to swing them comes out at 4 million suns, packed into a region that the orbits themselves prove is smaller than our solar system, containing nothing that shines. It's the Ophiuchus wobble again, the same trick that found our neighbour, performed at 4 million times the scale, and it earned Genzel and Ghez the Nobel Prize in Physics in 2020. The largest black hole in our galaxy and the nearest one were both weighed the same way, by watching something bright dance with something that isn't there. It's 26,000 light-years away, 17 times farther than our record-holding neighbour, and the stars closest to it, the ones astronomers watched whip around it at thousands of kilometres per second to weigh it in the first place, have orbited it stably for millions of years. Even the great Devourer, at the centre of everything, mostly just sits there, hosting orbits like any other mass. The universe builds black holes at every scale, from city-sized to solar system-sized, and at every scale it then does with them the same unremarkable thing it does with all its heavy objects. It sets things circling around them and lets the clock run. And the clock, for black holes, runs longer than for anything else that exists. Here's a thought to file under deep comfort or deep strangeness, depending on the hour. Last night, if you were with us, we met Proxima Centauri, the little red star that will outlive our sun 100-fold, still glowing trillions of years from now, after every bright star has gone dark. Black holes make even the red dwarfs look brief. A black hole loses mass only through the faintest process known to physics, a slow quantum whisper of radiation named after Stephen Hawking, so slow that for any black hole existing today, it's overwhelmed by the trickle of stray light and dust falling in. The numbers land beyond metaphor. A 10 solar mass black hole is expected to endure something like 10 to the power of 67 years. A 1 followed by 67 zeros against the universe's current age of not quite 14 billion, a 1 followed by 10 digits. When the last star in the last galaxy gutters out 100 trillion years from now, the black holes will just be getting started. There is an era coming in the impossibly far future that cosmologists literally call the black hole era, when these 100 million sleepers and all their cousins everywhere will be the only structured objects left, drifting through a dark that has finally caught up to them. The last things in existence still keeping their shape, still holding their locked rooms shut. The dark neighbor we hunted tonight isn't just older than every civilization, it will outlast the stars themselves, all of them, everywhere. We're not sharing the neighborhood with a monster, we're sharing it, briefly, with one of the only permanent residents the universe will ever have. Before we turn for home, it's fair to ask why any of this hunting matters. Nobody's in danger. We've established that thoroughly. The sleepers sleep. So why do astronomers give up their nights and space agencies their billions to find dark spheres that do nothing? The answer is that every black hole is a record, the most durable record there is, of a star's entire life and death. And right now our library of those records is nearly empty. When astronomers weigh a dormant black hole, like our neighbor in Ophiuchus, they're reading the final line of a biography. This is what remained when a star of such and such a size finished everything it would ever do. Collect enough final lines and you can reconstruct the rules of the whole story, which stars collapse and which explode themselves to nothing. How much of a dying giant escapes as wind before the end? Why the record holder's tidy orbit contradicts the textbooks, whether the galaxy's first stars really did grow heavier than today's, the way that 33 sun fossil in Aquila hints. These are questions about how the universe builds and buries its largest engines, and the dormant population is the unbiased sample, the full census, rather than the noisy few. That's the scientific stake in the fourth data release, sitting in its queue for the end of 2026. It isn't a stamp collection, it's the death registry of the giant stars, opening for the first time. And there's a quieter reason, the one that belongs to this channel. Think about what it means that we can do this at all. Every method in tonight's story amounts to the same act, noticing the invisible by its influence, a star that swings when nothing visible holds it, a background sun that brightens as unseen mass focuses its light, space itself trembling from a collision no telescope will ever image. We are a species that cannot see black holes, will never see them, not one, not ever, by the very definition of what they are, and we have counted them, weighed them, aged them, mapped their collisions across billions of light years and predicted, sight unseen, the one sleeping nearest to our own front door. 2 centuries ago, we didn't know how far away the stars were. 2 generations ago, black holes were a mathematical embarrassment most astronomers hoped would go away. Tonight, you know the address of the nearest confirmed one, the constellation it hides in, the ordinary star that orbits it, and the approximate distance of a nearer one nobody has caught yet. Every bit of that knowledge was pulled out of pure darkness by reasoning, patience, and the faint arithmetic of wobbling light. Whatever else is true of us, we are very good at finding things that do not want to be found. So let's finish the way we began, with the sky over your roof. Right now, tonight, the census stands like this. The nearest black hole anyone has confirmed sits 1,560 light years away in Ophiuchus, quietly holding a small yellow star in a 6-month orbit, doing nothing else at all. The second nearest, the 33 sun fossil, drifts in Aquila, 1,900 light years out, older than the Milky Way's spiral arms. Somewhere between 5,000 and 6,000 light years away, a lone 7-sun drifter is crossing the galactic bulge, caught once in the act of bending a stranger's light, never to be seen again. And far closer than any of them, statistically almost beside us, within the little sphere of space that holds the Big Dipper's stars and every constellation of your childhood, one more is almost certainly hanging in the dark, unnamed, unfound, unfindable for now. 60 kilometers of sealed silence that has been orbiting peacefully alongside us since before the Earth had a moon. It has never harmed us. It never will. It asks nothing, eats nothing, shines at nothing. A permanent resident of the neighborhood, keeping the oldest secret in physics, and the whole apparatus of human astronomy is bent this decade toward the single goal of learning its address so that we can do with it exactly what we do with everything else in the sky. Write it down, give it a name, and keep sleeping. Now, as we finally come to the end of tonight's hunt, let's fold the map closed slowly. We set out to find the closest black hole to Earth, and we found, instead, the shape of a beautiful, unfinished search. We met the record holder, the quiet 10-sun sleeper in Ophiuchus, betrayed by the lantern of its little yellow companion, close enough that its starlight left home while Rome was falling. We learned what these objects truly are. Not whirlpools, not hunters, but the sealed remains of great stars, city-sized, lightless, and still. We walked the history of the tricks, the X-ray screams that found the loud few, the false dawns that dissolved under honest scrutiny, the wobble machine that finally weighed the dark, the lensing lottery that caught a lone drifter crossing a lit window, the 4-kilometer instruments that feel space itself ring when the distant ones collide. We reasoned our way to the one that matters most and can't be seen, the statistically certain neighbor within some 80 light years, nameless and harmless among the stars you've known all your life. And we ran the fears to ground, one by one, until each dissolved into the same wide, protective emptiness we once cursed on the road to Alpha Centauri. The distance that keeps us from the stars keeps everything else politely away from us. It always has. And maybe that's the true gift of the black hole. Of all the strange objects we visit on these nights, they teach proportion. The scariest thing in the universe, examined patiently at honest scale with real numbers, turns out to be a neighbor of perfect manners, silent for 10 billion years, harmless for 10 billion more, destined to outlast every star in every sky. The universe holds monsters, that's true, and it holds them the way a museum holds swords, fixed, distant, and long past their wars. Nothing in tonight's sky is coming for you. The darkness between the stars isn't a predator's dark, it's the dark of a house late at night, full of sleeping things, held apart by distances so vast that touch itself is almost forbidden. And you, on your small, warm world, are tucked deeper inside that safety than any lock could ever put you. Thank you for joining me tonight on this long hunt for the closest black hole to Earth. From the wobbling star in Ophiuchus to the unnamed sleeper, somewhere among your familiar constellations. If this exploration eased the dark a little rather than deepening it, a like or a subscribe genuinely helps these quiet nights continue. And it's always good to have you here. The census is coming, remember? Within a couple of years, the fourth great data release will open and the record will fall, and some new, closer address will be written into the map. And when you hear that headline, whenever it finds you, you'll already know exactly what it means and exactly how little it should cost you in sleep. Somewhere out there tonight, closer than the stars of the Big Dipper, a sphere of sealed darkness is drifting through the same galaxy that carries you, keeping its secret, keeping its distance, keeping, in its own way, the same long night watch you're about to end. Let it drift. Close your eyes. The neighborhood is old and quiet and very well behaved. Sleep well tonight, beneath a sky that hides nothing that means you harm. Good night.